Hello students, welcome to Rasaayana Institute of Sciences. Last class we have begun with the introduction to periodic table, how to write the periodic table into various groups S, P, and D and F block elements we have written without saying. We have also numbered it. Later on we have taken the IUPAC nomenclature starting from 101 up till 118 elements. In this class I am going to give you the most important classifications that were given in the beginning, where they try to classify the elements into different types. So what are these different types and how important are they for the examination point of view, we are going to see in this class. Okay, so chemical periodicity, we also call it as periodic table of elements. Well, most of you may not have seen this type of periodic table where the elements are arranged in a three-dimensional spirals. So here if you are able to watch, starting from here, hydrogen, helium, lithium, and all the elements are in spirals, and this is arranged in a three-dimensional spiral. This is one of the earliest arrangements of the known elements. Whatever elements were known at that time, all those elements were arranging in this type. Okay, but this is not that successful because there is no periodicity in the properties. We want periodicity in the properties, the repetition. Once I know the repetition, okay, one element is behaving in a similar way to the other element, then I am trying to put them into a group. Once if I try to put them in a group, I will try to understand their properties. If I can understand the property of the first element, the second element property would be similar. So that should be the advantage that I should have, because it is not one or two elements we have. It is over 100 elements that we have. And it is not easy to learn the chemistry of all these elements. So we have to simplify. This was one of the earliest classifications. This one is like a spiral. If we have seen some seashells, the shape of the seashells would be like a spiral. This spiral is in accordance with Fibonacci sequence. Okay, you have something called as Fibonacci sequence or Hemachandra sequence in mathematics. It is on the basis of this Fibonacci sequence those spirals will be arranged. Anyway, they have considered such a spiral, and by considering those spirals they have arranged the elements starting from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and the remaining elements have been arranged. Okay, so here I'll just show, suppose if this is nickel, palladium and platinum, they are just matching, copper, silver, gold. Here they have given gadolinium, here they have given gold. So copper, silver, gold. But this classification is also not useful for us because that will not show any periodicity of the elements. There are many elements which do not fall exactly in a group. So this is also discarded. This is just one of the classifications of an elements. Okay. Yeah, this classification everyone knows because this is the most renowned or the most improved classification of the elements, periodic table, where you can find S block, P block, D block as well as F block. So we have to again come back here. Before coming back here, let us go into the history. Who is the first person who started to classify these elements? Father of chemistry. Here you can see Lavoisier. We call him as father of chemistry. So whatever elements that were known at that particular time, based on their properties means whether they are highly conducting or low conducting, high conductivity, low conductivity, or it is lustrous, is it shining or it is not shining. So when I say conductivity, let it be thermal conductivity or electrical conductivity, or am I able to make them into wires and sheets. So based on all these properties, they classified elements into two types. Whatever known elements were there at that time, they have classified into two types. We call them as metals and non-metals. But simply classifying the elements into metals and non-metals again will not give a proper idea for me. It is just like classifying these people into science students. When I say science students, what type of science have they taken? Did they take life science or did they take mathematical sciences? What type of sciences? Physical sciences? What sciences? So there should be more clarity. So this classification did not got more importance. So later we have another important classification. It is also generally asked in the exams. You might have seen this picture before. He is Wolfgang Dobreiner. Johann Wolfgang Dobreiner. We simply call them as Dobreiner. You need not call it as Johann Wolfgang Dobreiner. We can call him as Dobreiner. So with respect to Dobreiner, what he has given is, suppose if I take a particular set of elements, these particular set of elements have a connectivity with their atomic masses. He has taken 3 elements at a time. Okay, he has taken 3 elements at a time. Now, when I take 3 elements at a time, I am just classifying them into 1, 2, and 3. If I want to know what is the atomic mass of the central element, I do simply the average of the first and third element, atomic masses. So I take the atomic mass of the first element and third element, take the average of it. The average mass will be the mass of the central element. So he has given something called as law of triads. A very, very important point to be remembered. Dobreiner's law of triads. You just remember this point maybe about 20 or 30 times. Dobreiner's law of triads. So what is this law of triads? If I choose a particular triad of 3 elements, the atomic mass of the central element is the average of the first and third element. Okay, let me give you an example here. Here the lithium atomic mass is 7, potassium atomic mass is 39. So 39 plus 7, it would be about 46. 46 by 2 will be 23. So the atomic mass of the central element is the average of the first and the third element. Okay, he has taken several triads. Here I am just showing you 3 different triads. One is lithium, sodium, potassium. One is calcium, strontium, and barium, where the atomic mass of the strontium is the average of the calcium and barium. Atomic mass of bromine is the average of the chlorine and iodine. It is not exactly 79.9 that you will be getting it, but it will be very close. It will be very close to 80. So 79.9 is also very close to 80. Okay. Law of triads was successful only with few set of elements, not with every set of elements. So even this type of classification was not successful. But for examination point of view, in the match the following or in the different choices, one question regularly appears. Dobreiner's, you have to match with law of triads, law of octaves, or something else, something else. So simply remember Dobreiner's law of triads. Okay, triad is a set of 3 elements where the atomic mass of the central element is the average of the first and the third. Simple. Okay. Now let us work out a simple question. Predict the approximate density of cesium from the following data using law of triads. So what is the density? Here instead of giving atomic mass, they have given density. How to calculate it? Approach is very simple. Previously what we have done is, here we have potassium, rubidium, and cesium. So if I take this as a triad, whatever atomic mass, or if I consider density, the density of rubidium should be the average of potassium and cesium. Okay, so the density of rubidium should be the average of potassium and cesium. Here the question is, what is the density of cesium? This I want. Rubidium density, they have given it as 1.532. Potassium density, they have given it as 0.868 grams per cubic centimeter. Plus cesium density I want. So if I want cesium density, it is 1.532 multiplied with 2 goes to the other side, 0.868. So this is approximately 1.5 into 2 will be anywhere around 3, above 3. minus 0.8, so it will be close to 2 point something. Okay, so that will be your answer. So this is how the questions can be asked. Okay, so this is based on law of triads. The atomic mass or the density of the central atom is the average of the first and the last element of a taken triad. Right, let's move to the next slide. John Newlands, John Alexander Rena Newlands, but we simply call him as John Newlands. John Newlands has given a law called as law of octaves. Law of octaves. What is this law of octaves? Suppose if I choose musical notes, if I am an Indian, I will be choosing musical notes sa re ga ma pa da ni. Again sa will be repeating. So the eighth note is the repetition of the first. Sa re ga ma pa da ni. Again sa will be repeating. But in their musical notes they were having do re mi fa sol la ti. Again do will be repeating. Do re mi fa sol la ti. Do will be repeating. It means do is the eighth note, which is the repetition of the first note. So likewise what we are doing here is, whatever elements were known, these elements were classified as per these musical notes starting from 1 to 7. Whatever eighth element that I get, that eighth element has to be put under first element, because it is like the repetition. So the element properties will be repeating as that of the first one. Eighth element repetition of first element, the properties will be similar. Okay, so what is this do re mi fa sol la ti and what elements were classified by Newlands? Let us look. So here you can see Indian sa re ga ma pa da ni. Again sa will be repeating. But in Western we have do re mi fa sol la ti. Again do will be repeating. If you clearly look at the elements, hydrogen, helium is not given. After hydrogen is lithium, beryllium, boron, carbon, nitrogen, oxygen. Then fluorine, which is the eighth element, should be the repetition of the first element. Therefore it is kept under hydrogen. After fluorine we should have neon, but neon is not given. Directly we went to sodium, magnesium, aluminum, silicon, phosphorus, sulfur. After sulfur, chlorine is the repetition of the first element. So it is in the repetition of the first element we got hydrogen, fluorine, chlorine. Cobalt and nickel and bromine have also come in this group. Okay, so why they didn't consider the inert gases? Why I don't find helium, neon, argon, krypton or so on? The simple reason is, these inert gases were unknown at the time of John Newlands. So they were not included into his classification. Right? If I ask you a simple question, suppose if I give you some inert gases, okay, I give you helium, neon, argon, krypton, xenon and so on, radon and so on. If I give you this set of elements, can you still take this John Newlands law of octaves? Is it still valid? No, it is not valid. Because if I include those elements, then fluorine would not come under hydrogen. Fluorine would come actually here. Okay, because hydrogen, helium will be coming. Lithium, beryllium, boron, carbon, nitrogen. Here you would be getting oxygen and here you would be getting fluorine. Okay, neon will be coming in the place of magnesium. So everything would have been disturbed. So if at all inert gases were there, then John Newlands law of octaves would be invalid. Got it? Right. So this is John Newlands law of octaves. Dobrainer's law of triads. John Newlands law of octaves. Just remember, these are the important points. They will not give you the periodic table and they will not ask you whether these elements are in a particular group of John Newlands law of octaves or not. In such a way, usually questions are not asked, but they will be asking John Newlands, what is the law? Is it law of triads? Is it law of octaves? Then you have to remember John Newlands law of octaves. Dobrainer's law of triads. Okay? Right. Now here we have Mayer, who is a German chemist. He has given some curves called as Mayer's curves. So what he has done is, he has considered two things at a time. Previously they have simply considered a triad and then they have tried to consider atomic mass or density or so on. Later on they have considered law of octaves, but this person, what he has done is, he compared atomic volume with atomic mass. There was a comparison between atomic volume of a given element and the atomic mass. On this comparison, he has given some curves. He has drawn a few curves. On these curves, the elements that were falling at identical points, they were kept under a group. These are called as Mayer's curves. Okay, so when it comes to Mayer's, you remember them as curves. Mayer's curves. Mayer's curves are in accordance with the comparison of atomic volume with the atomic mass. Atomic volume with the atomic mass. Okay, just prepare for about 10 times. Lothar Mayer's curves. Let me show you. These are the Mayer's curves. So on the x-axis you can see atomic weight, on the y-axis you can see atomic volume, and different curves have been given. I'll just show one or two sets of elements. Suppose if I take at this particular point lithium, again at that highest point there is a sodium, again at the highest point there is a potassium, at the highest point there is rubidium, at highest point there is cesium. So if I can just connect all these elements, then I will keep them in a group. But there is lot of difference. If I am trying to take it linearly, you can just watch. If I try to take linearly, they do not fall under a line. Suppose lithium to sodium is connected. If I am just drawing a line, you can see potassium and rubidium are not exactly falling on a line if I compare it with the lithium and sodium. Likewise, different elements can be taken. Suppose if I choose fluorine here, I can connect fluorine to chlorine, chlorine to bromine, bromine to iodine. So all such identical points, they were connected and they were kept under a group. Okay, these are called as Mayer's curves. So Mayer's curves, these are in accordance with the comparison of atomic volume with atomic mass. Okay, law of triads, law of octaves, and Mayer's curves. Okay, remember three things. Law of triads, Dobreiner. Law of octaves, John Newlands. Mayer's curves. I'll just show the periodic table. You don't have to remember that periodic table. This was the periodic table given by Mayer's. This was the first periodic table where most of the main group elements were included. This was in 1864, but later in 1870 he included few more elements of D block. Later on he has given another periodic table, but this is not looking properly. You can just watch. Boron, carbon, nitrogen, oxygen, fluorine. It is like a period now. They were given like this. Boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium have come. Aluminium, silicon, phosphorus, sulfur, chlorine, potassium and calcium have been given here. Titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, that is fine. Arsenic, selenium, bromine, rubidium, strontium. So elements are not matching. If you properly see, these elements are not properly matching. But across this way, now you can just watch. Nitrogen, phosphorus, arsenic, antimony, bismuth. But in between you have vanadium, niobium and tantalum. Now we have vanadium, niobium and tantalum in a separate group. But these are like included: nitrogen, phosphorus, vanadium, arsenic, niobium, antimony, tantalum and bismuth. They have given separately, but anyway it is looking like a group. That is little bit confusing. Oxygen, sulfur, selenium, tellurium, that is fine. Chromium, molybdenum, tungsten, that is another group. But they are included like in one cell. Okay, so there is lot of confusion in Lothar Mayer's curves also. Okay, you just go through. And here you don't find any inert gas. Still you don't find any inert gas till this point. Now comes the most important person, the grand old man. He is Mendeleev. He is a Russian chemist. He is a very, I can call him as a genius, because why am I calling him as a genius is, he has done two things. First thing, he tried to classify the elements that everyone has done previously. But second most important thing is, he predicted a few elements. He has given some blocks. Suppose if this element was not there at that time, if there is any gap, he said in this gap there could be some element. If anyone discovers that element, the density of that element would be so and so. It would form so and so oxide. So these elements were predicted by Mendeleev. He has predicted some elements also. Not just classification, but he has also given a prediction of elements. I'll show the prediction of elements also. But according to Mendeleev, the single property he has chosen is atomic weight or atomic mass. So whatever properties that I choose of particular element, let it be across a period or a group, whatever elements that I am choosing, I have to classify the elements across a period on the basis of their atomic masses. So later he said, he gave a statement saying that the physical and chemical properties are the periodic functions of their atomic masses. So if I choose any element, let it be physical property or let it be chemical property, that depends on its atomic mass. Okay, not atomic volume or any other property, not density, but he has given a single property called as atomic mass. But very interestingly, this person Mendeleev, he got a dream, it seems. In his dream, he has seen all these periodic elements, and accordingly he classified whatever dream that he got. Accordingly he has given the periodic table. That is what he claims. You can look at the statement. I saw in a dream a table where all the elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction later seem necessary. This was the quote of Mendeleev. So whatever he saw in the dream, he just put it as it is. Just at one point he had to make a correction, which was necessary correction, and he has corrected it. So whatever table that he has given is called as Mendeleev's periodic table. Okay? At that time, it was the modern periodic table at that time, at his time. Now, the second point, what I told you is, he predicted elements. That was most important point. He predicted elements. So here I'll just give you a few predictions. Mendeleev's given name and the modern name, whatever modern name, this comes in the exam. So this table is important for us. This is Eka aluminium. Some of us pronounce, but it is not Eka, it is Eka aluminium. The small story behind it is, one of the best friends or roommates of Mendeleev, he was translating a Sanskrit text written by Panini, and he was translating into German language. So while he was translating, many Sanskrit words used to come. Mendeleev got very much attached with this Sanskrit. So he said, I'll be picking up few words from Sanskrit. What are these words that he has picked up? Eka. Eka means one. Dvi means two. Tri means three. Okay, so Eka, Dvi, three. It corresponds to 1, 2 and 3. So whatever he has predicted, accordingly, suppose aluminium was known, but gallium was not known at that time. Then he said, after aluminium, there will be one more element. If this element is discovered, this element should have so and so density, so and so molecular formula of an oxide, and so on. So he called it as Eka aluminium, one after aluminium. Boron, Eka boron. After boron, if at all there is one more element that will be discovered in the near future, that should have so and so properties. So he called it as Eka boron, one after boron. Eka silicon, Eka manganese, trimanganese, dvi-tellurium, dvi-cesium, and Eka tantalum. So these were the elements predicted by Mendeleev. Some of them perfectly match. Some of them perfectly match means after aluminium immediately is gallium. Okay, so Eka aluminium, after aluminium is gallium. In the examination point of view, they'll ask what is Eka aluminium. So you remember Eka aluminium is gallium. Okay, that is one important question for exam. Eka boron is scandium. Eka boron is scandium. But now Eka boron, one after boron, is not exactly scandium. After boron is aluminium. But Eka boron is scandium. Some predictions went wrong, but most predictions were found to be right. Okay. What is the next one which is correct? Eka silicon is germanium. This also comes under examination point of view. Eka aluminium is gallium, Eka silicon is germanium. These are important for examination point of view. Okay. Eka manganese is technetium, trimanganese is rhenium. So if I go to manganese group, manganese, technetium and rhenium. After manganese is technetium, after technetium is rhenium. So rhenium, maybe I should have called it as Dvi-manganese, 2 after manganese. But rhenium is called as trimanganese. So 3 after manganese, but anyway, he has predicted most of these elements. Dvi-tellurium is polonium. Dvi-cesium is francium. And Eka tantalum is protactinium. Okay, so these are the predictions done by Mendeleev for examination point of view. Eka aluminium, Eka boron, Eka silicon are important for examination point of view. So you try to remember 3. Eka aluminium is gallium, Eka boron is scandium, Eka silicon is germanium. Right? These 3 you try to remember for examination point of view. I'll show you the periodic table of Mendeleev, but before going into the periodic table, you just look at this. How beautifully he has predicted. He predicted Eka aluminium. I'm just showing you. This was the predicted element. Atomic mass, he predicted it to be about 68. Density was anywhere about 5.9. Melting point, he predicted it to be low. And oxide, if at all it forms any oxide and chloride, it should be E2O3. That element, E2O3. Element, Cl3. These were the predictions done by Mendeleev. And once the element was discovered, gallium, you can see its atomic mass is very close. 68, it was 70. 2 units difference. Density 5.9, 5.94, very close. Melting point, he said low. It is about 30.2 Kelvin, very, very low. And it forms an oxide called as E2O3. Gallium oxide, you can find Ga2O3. ECl3, gallium chloride was also found. So the element, whatever he predicted, most of them were matching. You can see another example of Eka silicon and germanium also, where atomic masses, densities, all of these things also match. Melting point is very high, and accordingly you can see 1231 Kelvin. Okay, so many things have matched, but few things could not. He should have definitely got a Nobel Prize, but he could not get a Nobel Prize. For the work that he has done is enormous. And this is the periodic table given by Mendeleev. You need not remember all this periodic table. Just as a glimpse, I am showing you this periodic table. You go through once. Twice he has given the table by making some changes. This is the periodic table. Yeah. Are there any limitations of Mendeleev's periodic law? The answer is definitely yes. There are a few limitations. What are these limitations? First one, anomalous position of hydrogen. So hydrogen, should I put it in first or should I put it in 7th group? That was a big confusion. So it is placed under 1A, but it has also matching properties with 7th group. It also has a matching properties with the 7th group. So should it be put under 1A or 7A? That was a big confusion. Okay, that was one of the limitations. Maybe I cannot call it as a defect, but a limitation. Okay. Second one, anomalous pair of elements. This is very important. What is this anomalous pair of elements? I am Mendeleev. I classified all the elements on the basis of their atomic masses. So on the basis of increasing atomic masses. Lower atomic mass, then should be followed by higher, then should be followed by still higher and so on. So it should be like in the ascending order. But you just look here, if I am taking argon, in the Mendeleev's periodic classification, after argon we find potassium. But the atomic mass of argon is 40, potassium atomic mass is 39. It is lesser than argon. But why did Mendeleev choose potassium after argon, though its atomic mass is less? There is no answer for it, because he has seen it in a dream. Accordingly, he has written it. But the atomic mass, it is not matching. 40 and then comes 39. It is lesser. Then we have cobalt and nickel. Cobalt is anywhere about 60. Nickel is anywhere about 59. It is not exactly 59. The closest values they were given. Tellurium 127.7, iodine 127. So tellurium having more atomic mass than iodine. thorium having more atomic mass than protactinium, but still thorium is given earlier than protactinium. So why are these given? Why are they have been put under in such a way? It was not properly explained. So that was another limitation. Next point. We have different isotopes. Suppose if I take hydrogen, hydrogen has got three isotopes: protium, deuterium and tritium. Atomic masses increases by 1 unit. Protium is 1, deuterium is 2 and tritium is 3. So if I consider atomic masses, then in the periodic table, should I include hydrogen, deuterium and also tritium? I have to place it according to the atomic masses. Then where is the place for deuterium and tritium? There is no place if I consider atomic masses. So that is another limitation of Mendeleev's periodic table. So these are the important limitations, or maybe you can call them as defects. The last defect that you can see is there is no proper position for lanthanides and actinides. There was no proper position given. In the modern periodic table, we will see it in the bottom portion, but no proper position was given for lanthanides and actinides. They were just included into the table. Okay, so these are the important limitations. Out of all these limitations, the most important one is anomalous pairs of elements. This is important for examination point of view. As I told you, he should have got a Nobel Prize, but very sadly he couldn't get the Nobel Prize, because the simple reason that was given was whatever work that he has done was earlier than 1900, but the Nobel Prize was given after 1900. So after 1900 again he has included some work so that he can get a Nobel Prize. But there were many people who were opposing Mendeleev. Most of the Russian scientists were opposed at that time because of Cold War. And one big person, chemistry, Arrhenius, you might have heard about him, Arrhenius equation. So he was in the Nobel panel later, and he was one of the persons who strongly opposed giving a Nobel Prize to Mendeleev, because Mendeleev did not accept Arrhenius equation, Arrhenius laws. Since he did not accept Arrhenius laws, this person was in the Nobel committee later, so he rejected, or he was completely opposing giving a Nobel Prize to Mendeleev. Okay, that will be the fights between the scientists. Anyway, coming to the last person, Mosley. What is this person done? What is this person done means? Mendeleev has given the classification on the basis of atomic masses. So he has taken that into consideration. He has done a small change, but that small change has brought a very big change. That small change is, instead of considering atomic mass as the basic unit, Mosley has done atomic number as the basic unit. So atomic mass was the basic unit given by Mendeleev, but atomic number was taken as a basic unit by Mosley. So instead of classifying the elements on the basis of atomic masses, Mosley classified the elements on the basis of atomic numbers. Simple, atomic numbers. Then the law given by Mendeleev was modified, stating that the physical and chemical properties are the periodic functions of their atomic numbers, not atomic masses, but atomic numbers. That was the only change done by him, and everything has matched. But anyway, he died at a very young age. He was shot dead. This was the periodic table given by Mosley's periodic table. Okay, so one point that you have to remember is the physical and chemical properties of an element are the periodic functions of their atomic numbers. That is the final statement. And Mosley's classification was almost the last type of classification based on atomic numbers. Later on we have again different classifications, but this is very, very important classification based on atomic numbers. Right? So where did we start from? We started from Lavoisier, who classified the elements into metals and non-metals. Later on we have Dobrainer's law of triads, John Newland's law of octaves, Mayer's curves, where there was a comparison between atomic volumes and atomic masses, Mendeleev's periodic law, Mosley's periodic law. Okay? Now, attempt a very simple and a small question. Eka aluminium and Eka silicon are known as gallium and germanium, aluminium and silicon, hydrogen and silicon, nitrogen and magnesium. Which of these? We have already studied. Eka aluminium is gallium. So just by knowing one particular element, gallium is not there in the first option. Therefore the option has to be A. Eka aluminium is gallium and Eka silicon is germanium. So the option is going with A. Which of the following group of elements is a Dobryner's triad? Osmium, iridium, palladium, ruthenium, rhodium, palladium, ruthenium, rhodium, platinum, sulfur, arsenic and tellurium. Which of these? Then some triads you have to remember directly. In this case the answer is ruthenium, rhodium and palladium. Ruthenium, rhodium and palladium, all of these belong to 4D group. So how to match them? Directly you remember the answer, because you cannot remember all these atomic masses. Here I have given you the atomic masses. Atomic mass of ruthenium is 101.1 mass units. Atomic mass of palladium is 106.4 mass units. So if I do the average, it is about 103.75 mass units. And what is the atomic mass of rhodium? It is about 103 mass units, 102.9. It is anywhere close to 103. 103 is close to 103.75. So these come under a triad. Okay. So which element that you will be remembering is ruthenium, rhodium and palladium will come under law of triad. Ruthenium, rhodium and palladium. The discovery of noble gases discarded what? Modern periodic law, Mendeleev's periodic law. Modern periodic law is Moseley's periodic law. Physical and chemical properties are the periodic functions of their atomic numbers. Modern periodic law. Mendeleev's periodic law, functions of their atomic masses. Lothar-Meyer's curves, it is the comparison between atomic volume and atomic masses. And Newland's law of octave. So which one should I consider? In the explanation I have given you, Newland's law of octave, if at all inert gases were there, then it can completely be discarded. So the option will go with law of octaves. Simple. Which of the following properties used by Mendeleev during the classification of elements in the periodic table? Is it atomic volume, atomic size, atomic mass, atomic number? A simple question, and the answer is also very simple. It is atomic mass. Okay, atomic mass. So this is a brief introduction about the various classifications given by different types of scientists. Along with this, we have other types of classifications like S, P, D, F type of classification, or left portion, right portion, middle portion and bottom portion. Or we have Bohr's classification, where we have classified the elements into some inert gases, representative elements and so on. So these types of classifications we'll see in the next session. Okay, so for this session, the most important questions for the examination point of view, try to remember the name of the scientist and the law that he has given. Okay, thank you.